All right, so I'm going to go through the FRQ that was for Unit 8, and I'm going to have this ready for you to retake either tomorrow, Friday, or Monday. Those will be the 3 days that you can retake it. So I'm going to go ahead and go through each part. That way you can kind of see what you may have made a mistake on originally on this FRQ. So first for part A, it says let R be the region bounded by the graphs F and G from 0 to 2. As shown in the graph, write but do not evaluate an integral expression that gives the area of the region R. So for the area between two curves, we're going to do like the upper bound curve, which will be this curve right here, which is y equals f of x. And then we're going to subtract the lower bound curve, which is y equals g of x, and we're going to integrate from 0 to 2. So we're going to have the integral from 0 to 2 of f of x, which is on top, minus g of x, and then we have dx there as well. So that'll be the area between those two curves from 0 to 2. And that's all you had to do. You didn't actually have to do anything additional. You just had to set it up. Now for part B, B is going to be probably the hardest part because we actually have to evaluate this. So it said let S be the region bounded by the graph G and the x-axis from 2 to 5 as shown in the graph. Region S is the base of a solid. For this solid, at each x, the cross sections perpendicular to the x-axis is a rectangle with a height equal to half its base and region S. Find the volume of the solid. Show the work that leads to your answer. So for this one, we're going to be integrating the region S from 2 to 5. So we're going to do integrate from 2 to 5. Now we're dealing with rectangular cross sections, and it says the height is going to be half of its base. So the base is just going to be this distance here, which would actually just be g of x. So that's going to be this function right here. So the base of that rectangle would be x squared minus 2x. And then the height of that's going to be 1/2 x squared minus 2x. And those are all being multiplied together, of course. So I'm going to go ahead and actually pull out the 1/2 just to make it a little bit easier. And then I'm going to write this x squared minus 2x squared because I technically have two of those, and I guess I should have a dx beside that. Now I'm going to go ahead and square this. So I'll have 1/2 times the integral from 2 to 5 of x to the 4th minus 4x to the 3rd plus 4x squared dx. And now I'm going to have to integrate this. So I'm going to end up taking up most of the space at the bottom to do this. So I'm going to have 1/2 still in front. And then I'm going to go ahead and integrate. So I'll have x to the 5th over 5 minus 4x to the 4th over 4, but that's going to just change into x to the 4th. And then I'll have plus 4/3 x to the 3rd. Okay, and I'm going to be taking this from 2 to 5. All right, so when you're integrating, you just add 1 to the exponent and then divide. So that's what I did for all 3 of those. So now I'm going to go ahead and plug this in. So I'm going to go ahead and plug in 5. So I'm going to have 1/2 times 5 to the 5th over 2 minus 5 to the 4th plus 4/3 times 5 to the 3rd. I guess I should have put those in parentheses. It doesn't necessarily matter for each of those. And then I'm going to be subtracting. Now I'm going to plug in 2. So I'll have 2 to the 5th over 5 minus 2 to the 4th plus 4/3 2 to the 3rd and then all of that's times 1/2. So technically you can stop right there, and that can be your final answer for that volume. Okay. All right, so now we're going to work on part C. It says write but do not evaluate an integral expression that gives the volume of the solid generated when region S, as described in part B, is rotated about the horizontal line y equals 20. So the horizontal line y equals 20 is going to be this line right here. And we're going to be spinning this area around that line. So we will actually have this gap here, okay? So we're going to have a washer instead of a disc. So we'll have a hole there. So we need to figure out what our big radius is and what our little radius is. Okay, our big radius is going to be the whole distance from the axis of rotation to the outside of what we're rotating. And that's just going to be 20. So that's what that big R of X is. The little R of X is going to be the distance between the axis and that inner bound that will create that hole in the middle. So that's going to be 20 minus the function g of x. Okay, because that is this function right here. So 20 minus g of x. So if we're going to set this up, we're going to have pi times the integral, and our integral goes from 2 to 5 because we're going from the endpoints of that section, so 2 to 5. And then we're going to start with our big R of X, which is 20 squared. And then we're going to minus our little R of X, which is 20 minus, whoops, not 22, 20 minus G of X squared. And then all of that will be integrated with respect to X. So you could simplify this down a little bit, definitely, but you can leave it just like this. So this could be simplified down into 400. And then you could also, instead of putting g of x, you could, of course, plug in the function there. Also, if you already established what big R of x are and little r of x are, you could just have those two squared as well. So there's a lot of different options on how you could actually set this up, but here's one option.